Starting with this lesson, and for the remainder of this course, our focus of study will be on polynomials, such as f of x equals 2x cubed minus 4x plus 5. And we'll study these polynomials from the perspective of a ring. And here's a definition. Let R be a commutative ring. Then the polynomial ring R bracket x is the set of all polynomials with coefficients in R. So here are some examples of polynomial rings. For instance, Z bracket x contains polynomials with integer coefficients. R bracket x has polynomials with real number coefficients. Z5 bracket x, polynomials, coefficients from Z5, and then more generally, Zm bracket x. So here's a concrete example. F of x equals 2x cubed minus 4x plus 5 is an element of Z bracket x because its coefficients, namely 2, negative 4, and 5, are integers. Here's another example. In Z5 bracket x, the polynomials 7x and 2x are considered to be the same because the coefficients get reduced mod 5. Therefore, the coefficient 7 is the same as 2 modulo 5. However, the exponents are not reduced mod 5. Therefore, x to the 7th and x squared are different polynomials in Z5 bracket x. Now here's a non-example. X to the minus 1, or 1 over x, is not a polynomial because in a polynomial, the exponents of x must be non-negative. Now, here is a general form of a polynomial in R bracket x, which we might use if we were, say, writing a proof about polynomials. So it looks like a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a sub 2 times x squared plus a sub 1 times x, or x to the first, plus the constant term a sub 0, where the coefficients a sub I are in the ring R. And as a matter of convention, we typically match the subscript of the coefficient a sub n with the exponent of the x term, so x to the n. And then we have a sub n minus 1 times x to the n minus 1. It just makes it easier for us to keep track of the terms and subscripts that way. Here's our first task. What is the degree of each of these polynomials? So if you could pause the video and answer that question, and then we'll go over them shortly. It turns out that the degrees of these polynomials are 3 and 2 respectively. It's the highest exponent in each polynomial. Here's a general definition. Let f of x be a non-zero polynomial in R bracket x. Then the degree of f of x is defined to be the highest exponent in f of x. For example, for the two polynomials above, we see that the degrees are 3 and 2 respectively because those are the highest exponents. Now, how about a polynomial, a constant polynomial, such as 7? Well, 7 can be rewritten as 7 times x to the 0. So the highest or the only exponent of that constant polynomial is 0. And there's nothing special about 7 here. In fact, all non-zero constants have degree 0. There are a couple of remarks about the degree of a polynomial. First is that the degree must be a non-negative integer because in a polynomial, the exponents of x can't be negative. We could have a polynomial with degree 0, however, and that's the case of a non-zero constant polynomial. Now, what about the zero polynomial? Well, the degree of the zero polynomial is undefined. All non-zero constants have degree 0, but the zero polynomial itself has an undefined degree. And soon we'll see why that must be true. And now please pause the video and work on day 28 classwork. And afterwards, we'll go over some of the problems and concepts. Here's an example from today's classwork. Let's consider these polynomials in z bracket x. So we view the coefficients to be integers. F of x has degree 15, and g of x has degree 8. Now, what do we get if we multiply f of x times g of x? Well, here it is. Its leading term will be 3x to the 15th times 6x to the 8th. Those are the leading terms from f of x and g of x. And then plus a whole bunch of lower degree terms. And now let's multiply these two terms together. And we know that the product will be 18 times x to the 23rd, but let's break that down a little bit. So by multiplying the coefficients, we get 3 times 6 times x to the 15 plus 8 using the law of exponents. Now here's the part that I like to highlight. 3 times 6 is not equal to 0 because z is an integral domain. In other words, if we have a pair of coefficients that are both non-zero, then their product will also be non-zero because z, being an integral domain, doesn't have any zero divisors. And therefore, we can conclude that the degree of f of x times g of x is equal to 15 plus 8. That's our conclusion. So to summarize, what we found is that the degree of the product of two polynomials is equal to the sum of the individual degrees. And we will generalize this in the next slide. And here's a generalization. Let f of x and g of x be polynomials in R bracket x, where R is an integral domain. So for example, z bracket x could be our polynomial ring, with the polynomials f of x and g of x both not equal to 0. Then, as we saw in the example in the previous slide, the degree of the product f of x times g of x is equal to the sum of the individual degrees. In other words, degree of f of x plus the degree of g of x. The proof of this theorem can be found in chapter 28 of the textbook, and that argument will resemble the calculation that we just did in the previous slide. Now, we will use this theorem to prove other theorems, and here's our first application. This is from today's classwork. We found that in z7 bracket x, the only units are the constant polynomials 1 through 6, which also happen to be the units of z7. And likewise, in the polynomial ring z bracket x, the only units were the constant polynomials 1 and negative 1, which again are the units of z. And in R bracket x, the only units are the non-zero reals, once again viewed as constant polynomials, and those are also the units of R. So here's a generalization. If R is an integral domain, such as z7, z, or the reals R, then the only units in the polynomial ring R bracket X are the units of R, viewed as constant polynomials. In other words, non-constant polynomials cannot be units in R bracket X. And now we're going to prove the theorem that we just stated. And here's the opening of the proof. Suppose f of x and g of x are polynomials that are units, and in fact, a multiplicative inverse pair that multiply together to be 1. And we're going to show that f of x and g of x are constant polynomials. And that will prove that all units of the polynomial ring R bracket X are constants, and therefore units of the coefficient ring R. Now, since f of x and g of x are multiplicative inverses of each other, they multiply together to be 1. Then how can we show that each of these must be a constant polynomial? Well, let's say, for instance, f of x weren't a constant. It had degree 3, and g of x had degree 2. Then their product would have degree 5. And that can't possibly be equal to 1, which is a constant polynomial of degree 0. Now let's generalize that argument. We can take the degree of both sides of this equation and obtain degree of f of x times g of x is equal to the degree of the constant 1. And the next step is where R being an integral domain comes into play, because we saw earlier that in that case, the degree of the product of these polynomials is equal to the sum of the individual degrees. And we also know that the degree of the constant, such as 1, a non-zero constant, is equal to 0. And therefore, we have this equality, degree of f of x plus degree of g of x is equal to 0. But degrees must be non-negative integers. So we have a pair of non-negative integers that add to 0. The only way that's possible is if we have 0 plus 0 equals 0. And therefore, we conclude that the degree of f of x and degree of g of x must both be 0, and therefore f of x and g of x are constant polynomials as desired. And that's the end of our proof. But if our coefficients do not come from an integral domain, then as we saw in the classwork, strange things can happen. For example, in Z9 bracket x, where 9 is not an integral domain, when we multiply 1 plus 3x by 1 plus 6x, and then we reduce the coefficients in Z9, so 9 is equal to 0 in Z9, and 18 also equal to 0 in Z9, then we see that the product is 1. In other words, we have a pair of non-constant polynomials that are multiplicative inverses of each other. And that's rather strange. Here's another example, this time from Z6 bracket x, where Z6 also not an integral domain. This time when we multiply 2 plus 4x by 3x squared, let's reduce the coefficients in Z6. So 6 is equal to 0 in Z6, also 12 equals 0 in Z6, and therefore their product is 0. We have a pair of non-zero polynomials, 2 plus 4x and 3x squared, that multiply together to be 0. In other words, we have 0 divisors in Z6 bracket x. Again, very strange indeed. Here's the takeaway. To avoid these strange things from happening, We like to work in polynomial rings R bracket x, where the coefficients come from an integral domain. And in fact, it's even better if the coefficients come from a field. So we like to work with Z7 bracket x or R bracket x, where R is the ring of real numbers. And that's what we're going to do from now on most of the time. And with that, this is the end of today's lesson, and I will see you next time.